that we are deciding can be assigned from 0 to 255. Then the values that we see, the maximum one, we assign it to be 255, and the rest of them we evenly divide them. So we will see that if the, let's say, value is 121.3, we say go to 121. And if it is 121.9, we decide go back to 121. So this is how we decide that these values that which are actually fluctuating, we decide that what they have to be represented. Now, please note, this is a continuous range, right? And we decide that it will be very discrete value. In other words, between point A and point B there is nothing. And then we also decide that what is the quantity, the value that we have to assign for point A and point B. Now, this decision that I want to say that this is 255, I want to say that this is 120, based on the number of bits that we are representing, is called quantization. So quantization actually tells you how discriminative the color representation or the tone representation will be. So what happens after I have sampled my data, I decide that what should be the value. Remember, the word quantization means we will lose information. So whenever we are quantizing something, it means that it is one way, you cannot get back. Of course, you can always get back by using the probability theory. You can estimate, but you will never get the exact value. That's why that later, when we are talking about compression, we will see that if we have in the building block the term quantization, it means that the compression is lossy. We can never get the actual value back. So in other words, if you have the analog image, and after you do digitalization, which means that quantization is involved, then you can never retrieve the original analog image back. Of course, there are lots of techniques which can give us the analog or similar to the analog back, and we can see, and you see that there is absolutely no difference. This is something that in image processing we call it psychovisual effect. Like you can see nothing from the difference point of view. You see that they are absolutely the same. That's why we have some quantitative metrics which you will learn in this course, something like peak signal to noise ratio, and we see that actually there are differences, but we cannot understand it. Now, is it good or bad that there are differences and you don't see it? It's great, right? It's great because you can sell it and no one understands that there are the differences. And this is how we are actually compressing quite a lot. I mean, we have the JPEGs, we have all those type of suffixes which are compressing the images. There are lots of loss and we don't see. However, there are some specific applications which cannot tolerate any type of loss. Medical images, right? You cannot compress and someone who has cancer, you say that you don't have cancer because you lost those information. Or let's say satellite images is very, very well known, because one star is 1 pixel, and if you compress it, you can just decline that there is no other Earth, because you just compressed it and you lost it, and you cannot retrieve it back. So some of the images, we cannot compress them much, because we cannot have this psychovisual effect inside it. But most of our daily life, we don't care. I mean, you want to put it on Instagram, who care about how much of the information of the hairstyles is inside there. So we can compress it as much as we want. So psychovisual effect on the daily life application is very, very cool. But we know that due to the quantization concept of quantization, we have one-way arrow. We lose it forever. We cannot retrieve exact values. Now, here we have the analog. Of course, this is an exaggeration. We have an analog image, and then what we will get after sampling and quantization of the image. In other words, you can see these curvatures. We don't have the curvatures actually, because everything is quantized. Everything has a single specific values and locations. So here you can see that we are putting, let's say, shading the different locations rather than some portion of the locations, because in the discrete form we don't have 1.5. We are either 1 or 2. So, and we have different tones, whereas you can see here how the tones are better. In the reality, what happens, your camera has, I don't know, a 14 megapixel, 20 megapixel, right? So it means that the image that you want to display on a very small screen, you are having millions of pixels. So in other words, you really do not understand that actual thing that you see is very pixelized thing, because the resolution is very dense, it's very, very high. Again, you could see this one in an old TV. I don't know if you had very old TV, those tube ones. If you go and sit very close, especially to the edge of the TV, you can see the dots. And you can see that everything is actually made of these pixels, these dots, which are not continuous. In other words, we don't have a curve. Everything is like a stepwise. However, from the distance, due to the high resolution, we just see everything in a very, very continuous form. Now, here we are talking about this slide. We actually get back to these very important slides when we are talking about the compression. It's mainly talk about how we are doing the quantization, and it talks about that how many pixels we need in order to represent an image. Quantization actually gives us this help that how much pixel you need. Why do I care about how much pixel I need to represent something? Because you have an internet package, let's say, and one gigabyte, and you can use that one. So it's important for you to know how, when you take an image and you are sending it, how many bits you are transmitting, because those gigabytes are counting those number of bits, right? Or let's say you need to transfer it. I don't know. You are a very famous person and you are in the space agency, right? And around the Earth, and you take a picture and you want to send it. It's very expensive to send it, right? So they are counting the number of bits. So it's important for you to know what is the quantization level that you want to use, how many bits you need to represent. Because if you are changing your quantization level, you can have actually different values. I think after this slide, I have a better table which tells you that how the number of bits actually affects. You can see the real numbers. I showed a picture of Obelix before, and I told you that if you go at any single pixels, you will see that it has an intensity value. This is actually a little bit of Lena, that beautiful lady. And if we zoom a lot into the fundamental part of an image, which is kind of a pixelized, you see that each of them is a number. This means that an image that we are dealing with is actually a matrix. That's why that mathematicians are usually very good people in image processing, because they know how to handle a matrix. If you know how to handle a matrix, it means that you know how to handle an image in theory, right? Now here is that table that I discussed, and I said that typically, in order to see that what is the size of an image, how many pixels do we need? We will get back to this table with a better point of view when we want to talk about the compression. So I just don't want to mess with your mind. Keep this on your mind. If you are increasing the quantization level, if you have more number of bits, visually we have more number of bits to be transmitted. If the number of bits, if the quantization level is 1, in other words, if I have 1 bit to transmit, what type of image do I have?